To perform the picket fence part of the experiment, you're going to use two pieces of equipment. So one of them is this picket fence, and it's just a strip of plastic with alternating black and clear sections. And the second thing you'll use is what's called a photogate. So a photogate is basically an infrared LED that's shining a light onto a sensor on the other side. So if you block that beam, a computer can keep track of that fact. So we're going to use this photogate in conjunction with the picket fence to measure what the acceleration due to gravity is. Now if you've got a jacket or something, it's useful to put that on the desk just to act as a cushion for the picket fence. The way in which you actually do the experiment, I'll show you how to use the program on the screen in just a moment, but to physically do the experiment, you put the photogate like so on the hutch, oriented sideways, and then you orient the plastic strip such that when you drop it, the black stripes are going to block the photogate's beam. So to do the experiment, you would start the program running, and as I said, I'll show you that in a moment, and then you just drop the picket fence through the photogate, like so. Okay, so I've shown you how to physically do the free fall experiment. Now I'm going to show you the program we use. So to begin with, I'll warn you that this program is a little more complicated than it should be, but regardless, we can use this for our purposes. So first of all, it may be called picket fence instead of free fall, but this is how it looks on your screen. And there's a couple of things we're going to need to change before we can take data. So if you look in this top corner here, there's a setting that says intervals to time. So what that means is how many spaces between the lines do we have on our picket fence object. So pick up your picket fence object and look at it, and you want to count up the clear plastic spaces between the lines. So not the lines themselves, but the spaces in between the lines. On my picket fence object, I've got 6 of these, so I can change this down to 6. And we also need to fill in this edge-to-edge distance. What that is you take a ruler and you need to measure from the leading edge of one black line to the leading edge of the next black line. So from one edge of the black line to the same edge on the next black line over. So front edge to front edge. And you measure that with your ruler. On my picket fence, it's 5 centimeters, but this number needs to be filled in meters. So I put in 0.05 meters for 5 centimeters. So now I'm ready to take data, but first I have to trigger the program, and that's done up here. There's this little white arrow in the corner. It's got a button beside it with 2 white arrows on it. We don't want to click on that. We want to click the button that has 1 white arrow. Once I've clicked this, then the program starts running and I can drop my picket fence through the photogate at my leisure. So I click on run, and now I can drop my picket object through the photogate, and now I've got my data on the screen. Now to begin with, it's showing me a distance time graph. It'd be nice to look at a velocity time graph because we are measuring acceleration and we expect our velocity time graph to be nice and linear. The program does give you that option. You come down here to this lower corner and there's a button that says switch graph, and if I click that, it switches between a velocity time graph and a distance time graph. So I can look at my velocity time graph and oh good, it's nice and linear just like I expected. There is one glitchy thing about this button that I want to warn you about, however. You'll notice right in the center of it, there's this double-headed arrow. If you click on that arrow, nothing happens. If you click anywhere else on the button, though, it functions normally. So just be aware you need to avoid that arrow, and all will be well. So we've got our nice linear velocity time graph, and now we want the acceleration. So the acceleration is over here. It's just listed for you, and we're going to compare this value to the known value, 9.81 meters per second squared, to see whether this experimental value agrees with the known value within the limits of uncertainty for this experiment. If for any reason you decide you want to retake your data, you hit cancel, and that brings back this white arrow in the corner. And so I can at this point click that and drop my picket object again if I want to. So for the first time this semester, you're going to have to write a conclusion. Most of the experiments we do this semester will have a conclusion that you need to write. Near the beginning of the semester, they give you this bullet list of things that go into the conclusion. So I'm going to go through this very quickly right now just to give you a good idea of what each of these things is. It's question 4 in your lab manual if you want to follow along. The first thing they ask for is they tell you state the objective, what were you trying to measure, and what is the hypothesis for this experiment. So the objective is just what it says. What were you trying to measure? So for example, for the free fall experiment, we were trying to measure the acceleration due to gravity. So you would just say that in a full sentence. What is the hypothesis for this experiment? Hypothesis is usually just going to be some variation on we expect our measured value to agree with the predicted value within uncertainty. So for most experiments, that's what you'll write when you say what the hypothesis is. It would just be something like, we expect our measured acceleration due to gravity to agree with the known value within uncertainty. The second thing that goes in the conclusion is they say state your values. State your measured value and your predicted value, and include their uncertainties and also their units. So again, in a full sentence, you just write it out. The third thing you put in your conclusion is they say state the percent difference between these values. Now that's a calculation you've already done at this point. When you get to your conclusion, you have this number. So again, you just write it down in a full sentence. My percent difference between these two values was, and you give your value. The next thing you need to do is you need to state whether your values agree with an uncertainty. So this is sometimes a little confusing. You've got a percent difference that you just calculated. That is the difference between these two numbers. It's a way to gauge how far apart they are from each other. The uncertainties, which you also have, are a measure of how big a difference you're allowed to have and still say that your values agreed well. So the way in which you compare two values is you look at your percent difference that you calculated, and you look at the sum of the uncertainties for the two numbers. So you add those together, so we get a total of 3%. We don't want our percent difference to be any bigger than that, because if the percent difference between these two numbers is larger than 3%, that means our values do not agree with an uncertainty. So you look at your percent difference and you decide whether it's less than the combined uncertainty of these two numbers. If it's less than the sum of these two, then you say my values agreed with an uncertainty. And if it's not, you say my values did not agree with an uncertainty. And it's a good idea to write down your logic, just to say because this number is less than the sum of these two numbers. The next thing you talk about is whether the theory is supported by your data. So basically, if your percent difference is less than the sum of the uncertainties, if your values agree with an uncertainty that is, then you can say that yes, the theory was supported by the data that you measured. The last thing you do is you have to identify what's called the largest source of uncertainty. So there's an acronym that they use, LSOU. And the largest source of uncertainty, it depends on whether your values agreed or disagreed with an uncertainty, what that is. So there's this acronym VAWU, V-A-W-U, that just means values agree with an uncertainty. So if your values agreed with an uncertainty, then your largest source of uncertainty is something you took into account, something you already knew about. So you would go back to your data table and you look at the percent uncertainties on all your raw data. Whichever one is biggest, that would be your largest source of uncertainty, but only in cases where your two values agreed with an uncertainty. If your values did not agree with an uncertainty, then the largest source of uncertainty has to be something you didn't take into account. So it might be friction or air resistance, or maybe there was something weird about your equipment. But if your values don't agree with an uncertainty, then you have to suggest your largest source of uncertainty was something other than the uncertainties you took into account on your raw data. So if the values agree with an uncertainty, your largest source of uncertainty is one of your percent uncertainties on the raw data. And if your values did not agree with an uncertainty, then the largest source of uncertainty has to be something else, like friction or some exterior force that affected the experiment. So now you're ready to look at the 3 simulations for this experiment. So as usual, you go over to the 1100 folder on your desktop, and you double-click that, and this week you go into the Lab 3 folder. And you'll find 3 simulations there. You're going to play all 3 of those. So I'll click on the first one to open it up. What this is basically is I can come over here and click Run, and it's basically going to throw me a little movie. You'll see 2 balls, and what will happen is one of them will drop straight down, one will be fired exactly horizontally, and you'll be able to watch them fall under the effects of gravity. So I'll click Run, and I'll click Stop as soon as it bounces, because we don't actually care about what happens after the bounce. If for any reason you decide you don't like the way this looks on the screen, you can redo it. So what you do is you click Reset, and the balls come back up here, but there's a slightly glitchy thing to the program where it doesn't erase all of this junk. So to clear the screen, what you do is you click Control H. So Control H clears the screen, and then you can run it again. So I'll click run, and again I'll stop it when it bounces, because we don't care what happens after the bounce. Now in your manual it says to sketch a stop action picture of these two balls. So basically to sketch what you see on the screen. There's a faster way to do this. If you look at the top of your keyboard, there is a button that says print screen. So if you press that down, it saves a copy of whatever is on the screen right now. And you can open up Word and then paste that in. So I can just click paste, and it puts that image into Word. So then you can print out 3 copies for you and your partners, and that's a lot faster than sketching it by hand. Once you've printed this out and pasted it into your book, they've got a few questions about how would you describe the horizontal velocity or the vertical velocity of the two balls. So you answer those questions, and then you're ready to move on to the next simulation. So you just close this guy, and when it says, do you want to save the changes, just say no. So you always say no to that. So we open up the second simulation, and what this little movie is going to be is that they've got a ball down here. It's going to be fired into the air at an angle, and it'll drop back down. So again, click run to run the simulation, and stop it once it bounces, because we don't care about that. And there's another slightly glitchy thing in that the program didn't draw the ball's first position here. So if I click reset, it redraws it, and it forgets to clear all the rest of this stuff, so that actually gives me a nicer looking picture. So once I've got the picture looking the way I want it to, again, click print screen, open up Word, paste it in, and then print off as many copies as you need. Then they ask you some more questions about this. So what happens to the velocity of the ball as it rises, and what's true at the top of its trajectory. They also ask you to draw 2 to 3 conclusions relating to the velocity and/or the displacement and/or the time at the end of the trajectory. So basically this place just before it lands. So these are questions that you can answer based on the theory that you've learned in class. So you're basically looking at the symmetry of the situation. For example, what could you say about the time it took to travel to here compared to the time it took to travel to the midpoint? Or what can you say about the vertical or horizontal displacements of the ball at this point compared to its displacement at the beginning? Likewise, what could you say about the horizontal and vertical velocity of the ball at this point, comparing it to what it had at the beginning? Then you can go on to the third simulation. Again, don't save the changes. Open this guy up, and it's going to be very similar, except that the ball will be fired in the air, and then it's going to come down lower than it started, so lower than the launch height. So again, I'll run this, and when it bounces, I'll stop it. And again, it won't draw the first one, so I'm going to click reset just to give myself a nicer picture. And just again as a reminder, if you want to clear the screen for any reason, it would be Control H, and then you could run the simulation a second time. So as before, if you're happy with it, print screen, paste it into Word, print it out as many times as you need. And then they ask you some questions about this one as well. So they say, where on the trajectory is the speed of the ball equal to the launch speed, greater than the launch speed, or less than the launch speed? You do not need these numbers to answer those questions. You should be able to do it based on the theory that you've learned in class. So again, no numbers needed, no calculations needed, just answer based on the theory. In this part of the experiment, you're going to actually use a Hot Wheels car as a projectile, and we're going to fire it through the air and see how far it goes. So on your table, you've got a brick and also a section of Hot Wheels track, and you take the track onto the brick and also onto the edge of the table to make a nice ramp. And then the Hot Wheels car will just slide down this ramp, like so. Now we're going to measure, the point of the experiment is to measure horizontally how far it goes. That's called the range. We're also going to calculate that value. So in your lab manual, on page 48, there's a table, and there's 4 things that they tell you to measure. The length of the car, so that means just the length of this guy from end to end. The height of the table, which you can measure with the meter stick you've been given. And the photo gate time, what's that? Well, here at the end of the track, we've positioned another photo gate. This is oriented in such a way that when the car goes through it, it blocks the photo gate. Now remember that a photo gate is just an infrared beam and a detector, so that allows a computer, or in our case, a little measuring device, to measure how long it was blocked for. So we're going to measure how long the car blocks the photo gate beam for. The timer that we're using should be on gate mode and on read mode, which means that the little lights should be on. If you need to reset the value at any time, you hit the red reset button and it should zero everything for you. And you can test this. What should happen is if you wave your finger through the photo gate, a number should come up on the screen. If you wave it through a second time, nothing should change. So it just stores the one value. And again, if you want to zero it, just hit reset. Now the reason why we need these first three things, the car length, the height of the table, and the photo gate time, is so that we can calculate theoretically what the range of this Hot Wheels car is going to be. And then the last thing we measure is the actual range. So the experimental value goes here at the end. These three are going to be used to calculate it. To get the reason why we measure the length of the car and the photo gate time here at the beginning is because we need the velocity of the Hot Wheels car as it's leaving the track. So velocity is just distance divided by time, right? So this distance, the length of the car, divided by the time that it blocked the photo gate for, gives you the velocity. So just distance divided by time gives you the initial velocity of this guy. And we use the height to calculate how far it would fall, or how long it would be in the air if we just dropped from the same height, which of course we can use to calculate how long it's in the air for, even when it's going horizontally initially. So I'll tell you about the equations used in a second. The last thing I want to tell you about is how do we actually measure the horizontal range of this guy. What I recommend you do is run the Hot Wheels car through this, see where it lands on the floor, and then you've got a piece of carbon paper. Tape that to the floor in such a way that you can flip up the carbon paper and see the dot that the car makes on the ground when it hits. So you tape this onto the spot where the car is going to hit. You zero your photo gate, run the Hot Wheels car through there, it hits the paper, and then you can flip back the carbon paper and use your meter stick to measure how far it went from the edge of the table over to the dot on the page. So that's how you get all of your experimental values. And as I said, I'll show you in just a moment some things to be wary of when you're doing your calculations. So now I'm going to talk about the equations that you use in this experiment. So the first thing you'll calculate is the launch speed of your Hot Wheels car. So how fast was it going when it left the track? And as I mentioned earlier, it's just going to be the length of the car divided by the time that the photo gate was blocked for. So velocity is equal to distance divided by time. The next thing you calculate is the time of flight. This is how long it's in the air for. The way we get this is we know from theory that the time of flight, if you launch the car horizontally and just let it drop under gravity, is exactly the same as the time of flight would be if you dropped it from that same height. So we calculate that, and you have to be a little careful here in that d is equal to the height of the table here. So it's changed its definition relative to what it was up here. So up here d was the length of the car, down here d is the height of the table. So the time of flight is going to be 2 times the height of the table divided by the acceleration due to gravity, all square rooted. Once you've got those two quantities, you can then calculate the horizontal range. So this is our theoretical horizontal range. This is how far we figure the car is going to go. Again, d changes its definition, so it's something to be a little careful of when you're doing the calculations. Over here, d was the length of the car. Down here, d was the height of the table, and over here, d is the horizontal range. But this horizontal range is simply going to be v times t. So this v that we calculated times this t that we calculated. So after you've gotten these quantities, you're also going to have uncertainties that you've calculated for all of them, and then you proceed to something that's going to become very familiar over the course of the semester. And that is, once you've got your values, you summarize them in a table. So you'd write down your values here with their units, plus or minus their percent uncertainties, and you put a title on the table that's worth marks. And then next, you would calculate a percent difference between your two values. So you compare those two, calculate a percent difference, and once you've got that, you could then proceed on to write up your conclusion. So remember that your conclusion consists of answering all of these points in your bullet list. So state the objective, what were you trying to measure? In this case, it was the horizontal range of the car. What's the hypothesis? Basically that the measured value is going to agree with an uncertainty with the value that we calculated. State the measured values and the predicted values with their uncertainties in units. State your percent difference that you just calculated, and then say whether your values agree with an uncertainty. So is your percent difference smaller than the sum of the two uncertainties? State whether the theory is supported by your data, and then finally you identify what your largest source of uncertainty is. And you identify a largest source of uncertainty regardless of whether your values do or do not agree with an uncertainty. If the values do agree with an uncertainty, then your largest source of uncertainty will be something you took into account. So you go and look at your raw data values. Whichever measurement you took had the largest percent uncertainty, that would be your largest source of uncertainty when the values agree with an uncertainty. If the values do not agree with an uncertainty, then the largest source of uncertainty has to be something you didn't take into account. So something like friction or air resistance, or maybe the track wobbled or something. In general, pick one thing. Choose the one thing you think is most likely to be your largest source of uncertainty.